This is the restoration of the world's first Ethernet bridge, the DEC LAN Bridge 100. Today on the Serial Port, we'll be disassembling, troubleshooting, and restoring this legendary device, and hopefully getting it back in working order. If you haven't seen our first video on the LAN bridge, be sure to check it out to get the full appreciation of the era that this bridge comes from and how it ended up changing the course for Ethernet. The standard LAN bridge was meant to bridge two 10-base-5 networks, but the unit we have is the DEBET-RH, which has a single AUI interface alongside a fiber optic interface using these SMA connectors. It was used to connect two bridges together across long distances upwards of 3,000 meters that wouldn't have been possible using coax. But as we saw in the first LAN bridge video, this one does not power on. We saw a small power draw when it was first plugged in, which then dropped to 0. There is no power switch on these units, so it should power up as soon as power is applied. Beyond that, the outer plastic shell is badly in need of cleaning, and we know that the boards are pretty dusty and grimy as well. So let's go ahead and get it disassembled. The outer plastic casing is held into place with 8 screws. There are 4 pieces to the plastic assembly: the bottom cover, 2 middle pieces, and the top cover. It looks like the case itself was manufactured by FF Industries on November 2nd of 1988. The metal chassis cover is held on with 24 screws. These units had to survive in harsh environments, so that helps explain why they were so well built. The design of the LAN bridge is fantastic. Everything is easily removable, making disassembly a breeze. Now we can get to work on removing the power supply. After removing 9 screws, the supply lifts out, revealing the fan tray. After removing the AUI bracket, we can see that it is bent, probably from being installed incorrectly at some point, so we'll need to address that. Next, we can take out the fiber optic transceiver. The transceiver connects via a large pin header, and it's just behind a smaller pin header, which is used for the version of the LAN bridge that has a second AUI port. If the fiber interface ends up not working, this might come in handy. And here's the main board, the real innovation in this amazing device. With the fan tray out of the way, we can get to work on removing the power inlet, voltage selector, and the circuit breaker. And finally, the main board can be removed. With everything removed, we can get started on the repairs. The very first item we need to address is the power supply. We know the LAN bridge will not power on, so we need to start from the basics. This is a large switching power supply from the mid-80s, and while its basic design is similar to any other switch mode supply, the components reveal the age it came from the monster primary side filter caps and the metal can switching transistors. The feedback and regulation circuit is extensive, despite there being just 3 voltage outputs, 5 volts at 16 amps, 12 volts at 3 amps, and negative 12 volts at 1 amp. Before attempting to power it on, we should do some basic checks. The main fuses are good, and the bridge rectifier appears to be intact. Spot checking the ESR of some of the capacitors shows that they are in good condition as well. We did find a discolored trace in a darker area on the PCB where it was exposed to high heat, but checking the corresponding components on the top shows no issues. There do not appear to be any shorts on the voltage outputs either. So let's give it a shot. And absolutely zero output. The primary side caps have voltage, so the AC to DC rectification is working, but we have nothing on the secondary side at all. Each of the primary side caps is charged at roughly 165 volts, and because of their arrangement, the voltage across both is a whopping 330 volts DC, which can be considered lethal, so lots of precaution should be taken. After powering off the supply, I drained the caps using a high power bleed resistor to make it safe to handle. My attention then turned to this part of the circuit, the PWM or pulse width modulation controller. The UC3527AN chip is responsible for creating the switching signal for the power supply, and in order to work, it has to have a startup source of power. That's provided by this transformer, rectifier diodes, 1000 microfarad cap, and a 7812 regulator providing a 12 volt DC output to the controller. Despite having 120 volts AC on the primary side of the transformer, there was nothing on the secondary side. So without power here, the PWM controller could never start switching the transistors to start the supply. So I desoldered the transformer and the secondary side looks fine, but on the primary side, not so much. The solder posts have come loose from the transformer housing, and as a result, the primary side windings have become detached. So while there was 120 volts AC to these posts on the board, it never actually made it into the transformer itself. The obvious fix here is to simply resolder the windings to the posts, but these are extremely fragile and thin wires, so they need to be handled carefully. They also have a thin coating of insulation that can be removed with high heat, so I've removed that before soldering. Ultimately though, we were able to get all 3 wires soldered back on successfully. Trying out the supply by itself, we actually get our 5 volt output. It seems to be working, but let's try with the fans and monitor the 12 volt output. We hear a bizarre noise, and it looks like the fans have seized up. We then hooked up 8 ohm loads to both the 5 and 12 volt outputs. And while our negative 12 volt is way out, it overall seems to be working. This is great news, but let's see if the motherboard works. We had to rearrange the boards a bit to get the cable between the boards in the right orientation, but here goes nothing. This is amazing. The LAN bridge actually seems to be working. We can see the LED cycle after about 30 seconds or so, indicating that the board appears to be operating just like the other LAN bridge we tested. Now that we've made some progress, we tested the ESR of the caps on both the motherboard and the fiber optic transceiver, and all tested good. So the only thing these boards need now is a good cleaning. Before we get to that though, we wanted to dump the EPROM data to have for safekeeping and for others in the future that may want to restore one of these, as the EPROMs presumably store the firmware for the LAN bridge. After removing the EPROMs, we loaded each into the XG-ECU T48 programmer and read the contents. In the program, we select the AM27128A EPROM and then start the reading process. After saving that, we swap the EPROMs and repeat the process. And we'll make these ROMs available for download on files.serialport.org for anyone interested. Thankfully, there's no major damage to the case, and it really just needs to be cleaned up. We can also take this time to straighten out the AUI bracket. We covered the exterior facing side of the bracket with painter's tape, and then used a bench vise to bend it back flat. After removing the fans from the tray, we saw these are EBM Pabst fans. And check this out, these were made in West Germany prior to the fall of the Berlin Wall all the way back in October of 1988. They are heavy and feel incredibly well made, but the fins on this fan seem to be actually touching the outer shell. And the other doesn't spin very easily either, so the bearings in both are definitely shot. And instead of buying new ones, let's see if we can repair these. We started disassembling one by unscrewing the hub from the outer case and removing the wire clip. In order to get these completely disassembled though, the connector needs to be depinned in order to be able to pull the wiring through the fan case. From there, we can remove the bearings themselves. The same process was repeated on the other fan. We measured the bearings so we could order replacements. They are two different sizes, with a smaller being a 604 and a larger a 624. With the fans completely disassembled, we then cleaned the blades and housings thoroughly. From there, we installed new bearings in both hubs, and then started reassembling the fans. The fan shaft is held into place with a tiny snap ring that looks irreplaceably custom made for this application. Oops. I ended up finding a substitute that was thicker than the original, but hopefully it will work. The second snap ring went on without a problem. Great. After reassembling the second and fiddling around with the screws, I was thankfully able to get both spinning freely and ready for testing. There was a little bit of a wobble, but they are working again, so we have success. With everything repaired and everything cleaned, we're ready to reassemble. After reinstalling the case, we're ready to test. We're utilizing the IBM PS2 Model 25 that we featured in other videos. We've got a DEC fiber to AUI transceiver connected to the AUI port on the NIC, and we're using an ST to SMA fiber cable to connect to the LAN bridge. And we've also got an AUI to 10 base T transceiver to connect to our LAN on the other port. So let's see what happens. And it does not seem to be working. We should be seeing the self-test complete and turn on this LED here. and we should see the activity LEDs on both port A and B. Checking the fiber transceiver on the IBM, we do see light from the transmit side, but on the LAN bridge, we're not seeing any output from its transmitter. We do see a link light when connecting to the 10 base T transceiver on the LAN bridge, so the AUI port at least has power. Assuming the fiber transceiver might be bad, let's try out the second AUI header on the main board. After removing the fiber transceiver, we verified the pinout of the AUI headers and then used a DB15 breakout board to connect jumper wires to the correct pins. With the transceivers in place, let's try this again. But again, we get nothing. This is odd because the behavior seems identical to the LAN bridge we tested in our first video. We did not see the self-test pass until both ports were connected to nodes, so we assumed that that would be the case with this one. Looking at the manual, the self-test goes through a number of steps to verify different components are working, starting with basic tests that mainly check the programmable ROMs and the memory, before moving on to the network and MAC address lookup circuits. The main board has a large number of devices, but we can figure out some of their functionality based on the manual. The board has two AM27128A programmable ROMs here. They store the firmware and self-test code. The heart of the bridge, the Motorola 68K CPU, can retrieve 16 bits of data at one time, but the EPROMs are 8-bit devices, so the firmware is likely split in an even-odd fashion between the two EPROMs, which allows the CPU to retrieve a full 16 bits of data in one memory cycle. Alongside those is the Zycore X2816A, which is used as the NVRAM to store bridge settings, but we're bypassing that with a dip switch setting, which forces the LAN bridge to use factory defaults. On the right side of the board, there is a Signetics PROM that stores the MAC address and a checksum, and it is stamped with a DEC logo indicating that this might be custom made. There are 4 6264 static RAM chips here, 2 for the program code and 2 for the MAC address status table, which is a smaller version of the full address table that is stored on this array of 6 6264s. There are 16 4164 DRAM chips responsible for storing packets, while the CPU and programmable array logic are busy forwarding packets between interfaces or looking up MAC addresses. Speaking of programmable array logic, that is implemented through these chips here and surrounding 74 series logic chips. And finally, the Ethernet interfaces are based around the AMD Lance and consist of several chips. We should be able to narrow down where the self-test is failing by looking for data activity on each component. We can make an assumption that the ROM is okay since the self-test seems to be running and cycling as expected. We can also eliminate the NVRAM as it is bypassed by the dip switch setting we referred to earlier. For the RAM test, we used an oscilloscope to check various pins on the memory chips. We can see the 6264 memory being accessed after powering up, but checking the Lance chips, we see no activity, indicating that the test is most likely failing before this step. And the 4164s aren't seeing any activity either, so it's not making it to the packet memory test. That means the test is likely failing at one of these steps. And so where does this leave us? Well, it could be that one of the memory chips is bad or failing, so ideally they all need to be tested. That will require a lot of desoldering, and we need a memory tester as well. So for the time being, this is where our restoration of the LAN bridge ends. We'll have to revisit this at some point in the future, but it wasn't a total failure. Remember, at first it wouldn't even power on, and the fans were completely seized, and it definitely looks a lot better after getting everything cleaned up. So in the meantime, let us know in the comments if you've got any other ideas for troubleshooting. And of course, thank you for watching, and we'll see you next time.